Hi there, Mr. Holcomb here with another episode of The Math Behind the Modules. Okay, lesson 9. Awkward. Who chose the number 360 anyway? Why are we calling this lesson that? Okay, classwork opening exercise. It says, let's construct the graph of the function y equals sine x degrees, where x is the measure of degrees of rotation. Okay, so before I go any further, I'm just going to say this right now, and then we'll talk about it more later. But when you see a degree symbol right there, that means it's going to be measured in degrees. If you don't see a degree measure there, then we are measuring in radians, which we're going to get to in this lesson. Okay, so in lesson 5, we described that the domain of the sine function is all real numbers and the range is -1 to 1. Use your calculator to complete the table below with values rounded to 1 decimal place, and then graph the function on the axis below. Be sure that your calculator is in degree mode. So this has already been done in lesson 8, so I'm not going to spend a whole lot of time on this. I'm just going to plow through. So you want to go into your calculator and hit mode and make sure you are in degrees, not radians yet. So here we go. So you just say sine of 0, and that's obviously over 1 up 0, and y is the sine, so it's going to be 0. And it says round to 1 decimal place. So that's just going to be 0. Okay. And then sine of 30 should be a half, 0.5. Sine of 45 is root 2 over 2. So sine of 45 should be that decimal, which is 0.7. Sine of 60 is root 3 over 2. Whoops. Sine of 60 is root 3 over 2. And what is the square root of 3 over 2? 0.866. That would be 0.9 rounded to 1 decimal place. Sine of 90 is 1. And then we're going to repeat these values getting back to 0. The sine of 180 is 0. So these are just going to repeat. So I'm just going to save time here. 0.9, 0.7, 0.5, back down to 0. And then 210 is in the third quadrant. Now we're going over and down. So sine is going to be negative. So it's going to repeat these numbers, -0.5, -0.7, yeah, that's right. -0.5, -0.7, -0.9, and 270 is -1. And then we're going to start going back down to up to 0. So -0.9, -0.7, -0.5, and back to 0 at 360 degrees. And now we're going to graph this. So we're going to plot the point 0, 0. And these are in increments of 10. This is a really nice graph compared to the one that we used last lesson. So these are 10 degrees, each square is 10, and I want 30 degrees. And then this says 50 though. So I spoke too soon. So, okay, so this is they're leading us to scaling. So they gave us this 50 to -50 for a reason. All right, so that actually should be a negative, by the way. So if I graph 30, 10, 20, 30, and I go up a half, well, this is 10, 20, 30, 40, 50. So this is 10. 1/10 is way down here. A half is like here. 45 degrees, this would be 40, halfway would be 45, is a little bit higher, but not much. Okay. And then 90 is 1. So, I'm sorry, 60 is 0.9. So 60 is right here. That's about 0.9 right there, almost 1/10. Okay. And then we're going to start going back down again, 0.7, which is or actually we need to get up to 1, and that is at 90 degrees, which is here. So 1 on a scale of 1 to 10 is way down here. And then 120, 100, 110, 120, we're at 0.9. And then 135, here's 130, here's 135, we're at 0.7. Okay, and then finally, where are we? 150, we're at a half. And 180, we're at 0. Okay, so this thing is coming up to this maximum and then going back down to 0. And then it's going to go the other way. So now we're going to graph 210 is here. Down a half is just a smidge right there. 225 is right here. And down a little bit more, that's a seventh, maybe right there. And then 240 is here. Down a ninth, 0.9. And then 270, we're at -1, which is being generous. There's probably not that high. And then 300 degrees, we're at -0.9. 330, 10, 20, 30, we're at 0.7. Oh wait, I skipped one. 315, 310, 315, we're at 0.7. 330, we're at 0.5. And 360, we're back to 0. Okay, so there is the graph. It almost looks like a straight line, just slightly coming up here and then slightly going down. And if I did that in my graphing calculator, let's just see what would happen. Clear y equals the sine of x. Okay, but I'm going to make my window the same as this one. So my x minimum, I'm just going to say -10, and my x maximum will be 370, just so I see it all. And we're going to scale it by 10. And then the y minimum is -50. Y max is +50. And we're going to scale that by 10 as well. Okay, and now when I hit graph, okay, that's about what we got on this graph right here. So they did this on purpose, and we'll discuss this on the next page. Okay, this is page 2, exercises 1 through 5. So before I continue, let's have a little discussion here. What do you notice about the graph that was created in the opening exercise? So if I go back, here's the graph that was created. I didn't connect the dots, but if I had, that is almost a flat line. And so to answer that, you would say, well, creating a useful graph is impossible on the set of axes provided. So they gave us a square grid where the x and y were both scaled to every square being 10 by 10. And graphically, that just was not appealing and not very useful. So just keep in mind that in lesson 30 from module 1, we performed transformations on a parabola, and it changed the horizontal scale. So, and how did we do that? So you can change a parabola. A parabola, the parent function is like this. If you make a fraction, it grows slower. And if you make a greater than 1, it gets steeper quicker, if you remember. And how did we do that? Well, we took the value in front of x squared, which is 1 over k, and we changed the scale factor k up or down to make it flatten or vertically stretch. So what horizontal scaling can we perform to compress the parabola y equals x squared to make a graph twice as narrow? And that would be to make the 2 in front. So we want to make it twice as narrow, then we would make the value in front of x squared 2 to make that go like so. All right, so what might be a reasonable transformation to perform the sine function to make this graph narrower? And the answer to that is any translation of the form y equals sine, and then instead of x degrees, put a k in front of that x for any k that's greater than or equal to 1. So it says that students may struggle with y equals sine 2x degrees or y equals sine 10x degrees. So do we know which transformation would be the best? Maybe we should stop and think about what we're going to transform this graph into before we proceed. Okay, so that's what we're going to do now. We're going to do exercise 1 right here. And it says set your calculator's viewing window to x being 0 to 10. So you just take your calculator. Hopefully you've already done this in your calculator. You have y equals sine x. And your window was -10 to -50, or -10 to 370, just to get that whole thing. And by a scale of 10, and x min -50 to +50, or y min -50 to +50 for the y. All right, so now it says set your calculator's viewing window. So to do that, you press this button here, window. We want x minimum to be 0, and we want the x maximum to be 10. And of course, we want to change our scale back to 1. And for the y minimum, we want -2.4. And the maximum we want +2.4. And again, I'm going to change this scale back to 1 here. And then when I hit graph, okay, so that was just 0 to 10. So plot the following functions in the same window. So I want to plot y equals sine x. So there it is. And then I want to go to y equals, and I want to do sine 2x and hit graph. Okay, so what's happening there? It's getting steeper quicker. Then I go back and I do y equals sine 10x. So we're trying to find a value that works. Is basically what we're doing here by trial and error. All right, so that one is increasing quicker and it's leveling off and flattening out. But as you can see, the graph is getting better. And now we're going to do sine of 50x. So sine 50x and graph. Okay, that one we are able to see starting here to here is one period and then the beginning of the next. So let's do one more, sine of 100x. Okay, so there's one period, two periods, and part of a third. So as you can see now, increasing our k in front of x is actually taking the sine function and compressing it this way. Okay, so now number one says, this viewing window was chosen because it has close to the same scale in the horizontal and vertical directions. In this viewing window, which of the 5 transform sine functions most clearly shows the behavior of the sine function? So when we're looking at these, obviously the first 3 it was getting better, but we didn't see one full period of the sine function until we got to sine of 50. So the answer to this is going to be y equals sine of 50 times x degrees, or y equals sine of 100 times x degrees. Okay, either answer is reasonable because both of them are showing at least one full period of the sine curve. Number 2 says to describe the relationship between the steepness of the graph y equals sine kx near the origin and the value of k. Okay, so it would make sense to try to get the steepness at the origin to be the same as the diagonal line y equals x, which has a slope of 1. Okay, so that is what would be our goal. So which one of these would have looking like a slope of 1? So now if I go to y equals, I know that the first 3 were not good answers. So let me get those off so it's not as cluttered. And then when I go back and graph just those 2, here's sine of 50x. and there's sine of 100x. And now you want to look at the steepness. So here is 1, and here is 1, and 1, 1 looks like it's about there. And this slope right here does look like it's about 1. So I would say it would be this curve here. This one's too steep. This one's going up and hitting here quicker. It's steeper. This looks more like a 1, 1 slope. So I would say sine 50x is better. Number 3 says, since we can control the steepness of the graph, y equals sine k times x degrees near the origin by changing the value of k, how steep might we want the graph to be? Okay. What is your favorite possible slope for a line through the origin? Okay, so I made a mistake there. This should be here. It would make sense to get the graph y equals x slope of 1, but I want to answer this other question as well. Okay, so to answer 2, describe the relationship between the steepness of the graph near the origin and the value of k. As we increase k, the steepness of the graph increased near the origin. Okay, and that's what I was explaining with the graph over here, but I didn't paste in the right answer. And now, what would be the favorite possible slope for a line to go through the origin? It would make sense for that slope to be y equals x, which has a slope of 1. All right, number 4. In the same viewing window on your calculator, plot y equals x and y equals sine kx for some value of k. Experiment with your calculator to find a value of k so that the steepness of y equals sine kx matches the slope of the line y equals x near the origin. You may need to change your viewing window to 0 to 2 and y 0, 1. So let's do that first. I'm going to change my window from 0 to 2 on the x-axis. And for y, I'm going to go from 0 to 1. Okay, so then I'm going to hit graph. So there we're just seeing 2 squares in the coordinate plane. And so we are going to choose just one now. So I'm going to hit y equals, and I'm going to turn off sine of 100x. And we're going to start with 50. So there's the sine of 50x. Okay, and I'm going to now graph y equals x on the same coordinate plane. Y equals x will now be graphed next to it. So notice y equals x. Here's 1, 1 up here, and this is sine 50x. So if you click trace, it will put the cursor on one of these lines and it will tell you the equation. Sine of 50x. So 50 is not steep enough. Notice it's below y equals x. So now I can go to y equals, and I'm just going to delete these other ones. Okay, so I just erased all of those and I put sine of 60x in for y1 and x for y2, just so I don't have to keep scrolling down. And now when I graph this, am I getting closer to y equals x? So there's y equals sine 60, and there's y equals x. And that almost looks perfect right there. So I would say y equals sine 60 looks pretty darn good, okay? The teacher's edition says something else, and I'll show that. Okay, so they say sine 57x. So now I'm going to go back and I'm going to change that to sine 57 and just see what does happen. So sine 57x and hit graph. So there's sine 57x, and there's sine of x. So near 0, they're saying that looks closer. So, okay, sine of 57x it is. Okay, page 3. Let's discuss something first before I continue on to what you see on your page 3. It says, which values of k produce graphs of y equals sine times k of x that are close to the graph of y equals x near the origin? We just did that. So it should be near k equals 57. And it looks like choosing k equals 57 is close to what we want, but why 57? Something is strange here. And indeed there is something both surprising and natural about the value of k, of what the value of k truly is. First, let's review our basic system of measurement for rotation. We could take the entire circle as the unit of rotational measure, and this is known as a turn. Then a rotation can be expressed as a fraction of a turn. For example, a quarter of a turn would correspond to a right angle, and a half of a turn would correspond to a straight angle. Instead, we more commonly use a small unit called a degree. We divide the circle into 360 arcs of equal length, and then the central angle subtended by one of these arcs has a measure of 1 degree. Then a turn measures 360 degrees. Okay, so that's what we do for the circle. And it says, who came up with our current system of using 360 degrees in a turn? Well, remember the ancient Babylonians who made all of those astronomical observations that led to the discovery of trigonometry? They are also the ones responsible for our system of measuring rotations and angles. It appears that the Babylonians subdivided the circle using the angle of an equilateral triangle as the base unit. Since they used a base 60 number system, they divided each angle of the equilateral triangle into 60 smaller units, each with a measure 1 degree, giving 360 degrees in a turn. Each degree is subdivided into 60 minutes, and each minute is subdivided into 60 seconds. For our purpose now, using 360 degrees in a turn is cumbersome. Instead of basing our measurement system on an arbitrary number like 360, we will instead use a system in which the measures of angles and rotations are determined by the length of the corresponding arc of a unit circle. Okay, so here's what you see on your page. A circle is defined by a point and a radius. If we start with a circle of any radius and look at a sector of that circle with an arc length equal to the length of the radius, then the central angle of that sector is always the same size. Okay, did you hear that? This is super important. So what we're saying is, this radius is 1 centimeter. This radius is 1 centimeter. And this arc length is 1 centimeter. So in other words, if I took this arc length and let me draw a segment. So let me draw a radius. Okay, so there's a radius right there in red. So if I now take that and rotate it 180 degrees and don't change its length, so let me lock it. Allow move and rotation. So if I take this now and don't change its length and rotate it, here I move it out to here, and rotate it 180 degrees. It's not letting me rotate it. Okay, so, it did not allow me to rotate it. So what I did was, just let me explain this to you. The distance from here to here was 1 centimeter. Obviously, this is not drawn to scale. So therefore, I drew a circle centered at the point of tangency to the center of this circle and drew another radius over here. So this distance equals this distance, which I don't need anymore. I don't want that one, but this is also a radius here and it's equal to this one. And now if I get rid of this circle, think of this red line right here being a point going from here to here and rotated 90 degrees clockwise up to here. So if I straighten this arc out, that's where it would be. Okay, that is also 1 centimeter. That's what they are saying here. So a circle is defined by a point and a radius. If we start with a circle of any radius, look at a sector of a circle with an arc length equal to the length of the radius. So that's that there. Then the central angle of that sector is always the same size. So then if I took the length of this and did the same thing. Okay, so what I've done again is drawn a circle here centered at the point of tangency with a radius of the same radius we already have, and therefore drawing a radius up here would be equal to this radius. That's why I'm drawing these circles like so, and I did it over here. So now, as you can see, as the circle gets larger, this length also gets larger. In other words, if I had a 2 centimeter radius here and a 2 centimeter radius here, because this is 2 centimeters, because if I straighten it, it would equal both of those, then the angles are always going to be the same. Okay, we define a radian to be the measure of that central angle and denote it by 1 radian. So just whenever you hear the word radian, think of this angle formed by a circle's central angle where the angle intercepts an arc that is the same length as the radius. And therefore we call that angle measure a radian. So thus a radian measures how far 1 radius will wrap around a circle for any circle. It takes 2 pi radians, or approximately 6.3 radius lengths. Actually, it's 6. Well, we'll leave it at 6.3 for now. Degrees, radius lengths to wrap around the circumference. In the figure, 6 radius lengths are shown. So here's 1, 2, 3, 4, 5, 6, and we come up by this 0.3 short. So use a protractor that measures angles in degrees to find an approximate degree measure for an angle with a measure of 1 radian. So now if I get my protractor out and bring that down here, and I'll use the largest circle because it's easier. And when I do that, notice where it is. So if I click on here and I bring this up to my angle, notice where it is. It is at approximately 57 degrees right there. Okay, so 1 radian is approximately 57 degrees. Okay, so we find that the degree measure of any angle that has a measure of 1 radian is approximately 57 degrees. Now remember, we did the sine of 57 degrees and notice that that was a slope of 1 close to the origin in our graph of our sine curve. Okay, page 4, examples 1 through 4, convert from degrees to radians. Okay, so before I do that, rather than just giving you a formula for conversion, we need to know where that formula comes from. So on the prior page, it said 1 full rotation in radians is 2 pi. So if we start here at 0 and we rotate all the way around, this is also 2 pi radians. So if this is 2 pi for 1 full rotation, a half of a rotation is pi. And then if we only go up to here, that's only a quarter of a rotation, or half of pi, because this is pi, this is halfway to getting here. So this would be pi over 2. And then this would be 3 pi over 2, 3.5 pi, and then 2 pi. So those are just the basics there. There are more in between. And so converting from 45 degrees, what they're saying is, I'm just going to do this for the first example, I think. Let's make that line, I don't know, purple. So 45 degrees is right about there. So if I broke this up, and that's another halfway between the two 90s, if you will, halfway between. Now I've just made 8 equal sectors. So this is 45 degrees. Well, how much of a circle is that? 1, 2, 3, 4, 5, 6, 7, 8. So it is 2 pi divided by 8, but that reduces to pi over 4. And that's what I'm going to use. So I'm just trying to give you a sense of where these are coming from. All right, so this is pi over 4. So pi over 4, pi over 2, or 2 pi over 4, which reduces. This would be 3 pi over 4. 4 pi over 4 is 1. This is 5 pi over 4. 6 pi over 4 reduces to 3 pi over 2. And this is 7 pi over 4. And this is 8 pi over 4, which reduces to 2 pi. And we can keep doing that over and over and over, but just for this purpose, this is where I'm going to stop. So convert from degrees to radians, 45 degrees. So think of this as this: 45 degrees equals 1/8 of a turn. Okay? And then we're going to substitute, and that is 1/8 of 2 pi. And that is going to equal 2 pi over 8 or 1 pi over 4. And that's what it reduces to. And that's what I was just trying to explain. And you also want to put the word radians at the end. So it's pi over 4 radians. So this would be 2 pi radians. So once we go from turn, to call it radians. So that's what we're going to do in this page. So now it says convert from degrees to radians of 33 degrees. Well, 33 degrees equals 33 over 360 turn. Okay, remember a degree is a portion of a full rotation. So I could have said 45 over 360, but if I go in my calculator and say 45 divided by 360, I'm going to get 0.125. Which is 1/8. Okay? And that's where that comes from. So that's where this 1/8 came from. So you don't have to do this unit circle with all these breaks, because where's 33 degrees and so on. So we have 33 over 360 turns. Well, that's going to equal 33 over 360 times 2 pi radians. Okay? So this is going to equal 66 pi over 360 radians, which equals half of 66 is 33. And half of 360 is 180. So we can reduce this down, in other words. So 33 times 2 is 66 pi radians over. So then I just take my calculator and say 66 divided by 360. And I get 0.183. And if I hit math, enter, enter, it will give me my reduced fraction, which is 11 over 60 pi radians. Okay, so there's the answer. One more time, actually 2 more times. Convert negative pi over 3 radians. Well, converting a negative pi over 3 radians, okay. Negative just means we're rotating in the opposite direction, so don't let that bother you. So let me change color. So negative pi over 3 radians. So we're converting from radians to degrees now. Negative pi over 3 radians equals, well, how much of a turn is pi over 3? So looking back at our unit circle here, I don't see a pi over 3. We'd have to cut this circle into thirds. So let me do that. Okay, so I went back to the basics. We're going to leave those 4 there all the time. And remember, pi is right here. So how many thirds is pi? It's 3 pi over 3. Okay, so if I split this like, let me use a straight line and purple. So if I split this evenly into thirds, it'd be about here and say there maybe. So what I'm basically saying is if I did not have these red lines here, let's get rid of them for now. And now I have, let's leave that one. So there's 3. Oops. And then we're going to do it again here. Let's do purple. So from the center, I'm going to continue over like so and over like so that these are equal. So I just need to fix these a little bit. They're not going to be perfect, but you'll get the idea. So there's 1/3, 2/3, 3/3, 4/3, 5/3, 6/3. So did you hear what I just said? So what I really need, all I really needed to do is say 2 pi, would this be equivalent to what over 3, or multiply that by 3 over 3, and that'd be 6 pi over 3. Okay, so this tells us that there are 6 1/6. It takes 6/3 to make 2 pi. So with that being said, pi over 3 equals 1/6 of a full rotation. It's a sixth of a turn. So 1 radian is going to equal 1/6 turns. Okay. And then we say that that's going to equal, and there should be a negative there, negative 1/6 times 360 degrees. And so that's going to equal a negative, and 6 goes into 36 6 times, and then there's a 0. So that is going to equal negative 60 degrees. All right. Next one, 19 pi over 17 radians equals some number of turns, some fraction of a turn. Okay, so this one's a little tricky. 19 over 17, 17 won't go into 360 evenly. So you see that pi right there? Keep in mind that in this circle up here, that was right here, pi, not 3 pi over 3, which is the same, but pi. Pi is a half a turn, is it not? So how about we just say this? You take that 19 over 17 and represent this pi as a half a turn. That makes sense? And so that is going to equal 19 over 17 times 2, which is 34. And instead of saying turns now, times 360 degrees. Okay? And when I go into my calculator and I take 19 divided by 34, enter, times 360, I get approximately 201 degrees. Okay, hopefully that made sense to you. Pi, remember, is a half a turn. Okay, page 5, exercises 6 and 7. Okay, now the lesson is coming together. Okay, there's a method to the madness here. And it says to complete the table below, converting from degrees to radians or from radians to degrees as necessary. Leave your answer in exact form. Okay, whenever they say to leave the example in, or the answer in exact form, it means if there's pi, leave it in terms of pi. Do not put pi in your calculator and come up with a decimal approximation. Okay, so 45 degrees, we already did, it was pi over 4. 120 degrees. So remember, 120 degrees would equal 120 out of 360 turns, if you will. And that will equal, well, 12 goes into 36, the 0's cancel, 12 times 3. So that's going to be 1/3 times 2 pi radians, right? One full rotation is at 2 pi radians. And then that is going to equal 2 pi over 3 radians. Okay, so that'll be 2 pi over 3, because if it's involving pi, leave your answer in that form. Now we're going the other way for this one, and it's going to be negative 5 pi over 6, and that is going to equal, and when we're going from, I should say radians here, that is in radians if you see the pi symbol, radians equals negative some terms. Okay, so how many turns is 5/6 of a circle? Okay. Okay, so again, we have that pi value right there. Remember that. That would be 5 over 6 times 1 over 2, because pi is in half a rotation. So that is going to equal negative 5 over 12. Okay, times 360. So that is going to equal, well, 12 will go into 36, 360, 30 times. So 5 times 3 is negative 150 degrees. Whoops, 150 degrees. So this would be negative 150 degrees. And somehow this got moved. There we go. Okay, negative 150 degrees. And then we're going to do 3 pi over 2. All right, so I'll do that over here. So 3, oh, I see everything got moved. 3 pi over 2 radians equals 3 over 2 times pi terms. And that is going to equal 3/4 of 360 degrees. 4 goes into 36 9 times. So it's times 90. 9 times 3 is 270 degrees. 270 degrees. So remember 3 pi over 2, 1 pi over 2. If I go back to my circle up here, 1 pi over 2 was here. Pi, 3 pi over 2 was here. I just had erased that vertical line there. 3 pi over 2 is 270 degrees. It checks. Okay, so now 450 degrees. So we take 450 degrees equals 450 over 360 turns, which will equal 45. 9 will go into 45 5 times. 9 will go into 36 4 times. So it's 5 over 4 times 2 pi radians, which would equal 10 pi. Where did I get 0 or 11? 5 times 2 is 10 pi over 4 radians. And that reduces to 5 pi over 2 radians. Okay, I don't need the word radians because it's the table with the radians in the top. Okay. Okay, so x degrees. Follow this. X degrees equals x over 360 turns, which equals and then we're going to take turns, and it's going to still be x over 360 times 2 pi radians. Okay, so it'd be the 2 is going to reduce to 360 now, and we're going to get x pi over 180 radians. Okay, and I can rewrite that as pi over 180 times x radians. So this will be pi over 180 times x. Okay, that is really important that you understand this now, because now look what we have. We have a formula. So whatever the x or whatever the degree measure is, all we have to do is multiply by pi over 180, and boom, we will get these values. Okay, so now let's do the last one here, and I'll erase this here, and we're going to model this example above us because it's radians to degrees. And that's what we're doing. So we have x radians equals, so this was 3 pi over 2, which is right here. And since a radian is, let's think about this. Let's use a degree with radians. What did we do? X radians, 3 pi over 2 radians equals 3/2 times pi. So now we have x radians, and that is going to equal so many turns. And how many turns is that going to be? Okay, so when we're going from radian, what is a radian? What is a full rotation of a radian? Notice over here we're putting in 2 pi. And over here we're putting in 360. But we're converting from radians to degrees. And so we want to know that x radians, 2 degrees, is going to be some portion of 2 pi. So that'd be like x over 2 pi turns. And that is going to equal x over 2 pi, some portion of a full rotation in radians, times 360 degrees. Okay, so this 2 and this 360 will reduce, and we're going to get, actually I've got this backwards. It's going to be 2 pi divided by a portion of 2 pi, like this. No, that's not right. I had it right the first time. Think of that as 360 over 1. Okay, that's better. So this is going to reduce. 360 is then going to be 180 degrees over pi. And then the x is going to be multiplied outside. Think of that as over 1. So x radians is going to equal 180 degrees over pi times some x, which was the radian. Okay. So these last two, this right here, you want to highlight. This is the whole key to this lesson right here. So I'm going to highlight this, fill yellow, and I'm going to go to properties and show it through. There we go. So that is the whole key to what we just did to find out how to convert from radians and degrees. So if you're going from degrees to radians, you multiply by pi over 180. And if you're going from degrees to radians, you multiply 180 over pi. So number 7, on your calculator, graph the function y equals x. Okay, so I go to my calculator and I'm going to go to turn it on, clear, y equals, clear, clear, and I'm going to put y equals x, and sine of 180. So I need another parentheses. Sine of 180 divided by pi, and pi is second, this caret, pi is right here. Close that parentheses, put an x, put another parentheses, and graph. Okay, so there's the line, and there is the sine of pi, 180 pi times x. So near the origin, the slope is the same. The slope is 1. So what is the decimal approximation of the constant 180 over pi to 1 decimal place? And then explain how this relates to what we've done in exercise 4. Okay, so the graph of y equals sine 180 pi times x is 180 over pi times x is nearly identical to the graph of y equals x near the origin. So as you can see, they're right there on top of each other. And then finally the sine slows and comes to a stop and then declines. Okay, so on the calculator, we see that 180 divided by pi. I haven't done that yet. So if I take 180 divided by pi, I get 57.2957791, which is about 57.3. So that sine of 180 pi x is approximately the sine of 57x degrees. This is the function we looked at in exercise 4 earlier in this lesson. Okay. Okay, page 6. If degrees are changed to radians, then the expression sine of 180 over pi times x degrees, where x is measured in degrees, becomes sine of x. Notice there's no degree symbol anymore, where x is measured in radians. Then one period of the graph of y equals sine x on a grid with the same scale on the horizontal and vertical axes now looks like this. So then we go from -1 to 1 on the y-axis, and 0 to 2 pi on the x-axis. So from this point forward, trigonometric functions will always be graphed using radians for measuring rotation instead of degrees. Besides the discovery that the graph of the sine function is much easier to create and use in radians, it turns out that the radians make many calculations much easier in later work in mathematics. So from this point forward, pre-calculus and calculus, you are going to start using radians, or you're going to use radians from this point forward. Okay, so now on to this discussion. Okay, so here is the unit circle. And if you look at this, on the inside, it is in radians. And on the outside, it is the cosine and sine values of those radians. So pi over 6, pi over 4, pi over 3, instead of 30, 45, and 60 degrees. Okay, so 30 degrees is pi over 6. 45 degrees is pi over 4, and 60 degrees is pi over 3, and pi over 2 is 90 degrees, pi is 180 degrees, and so on. So the values inside are now in terms of pi or radians, and therefore the outside stays the same though, because we have the sine of the same angle measure, but now it is in radians. So pi over 6 radians, the sine of pi over 6 is √3/2. Okay, and I can check that in my calculator. So now if I say, remember this was 30 degrees. So if I say the sine of 30, I'm going to get a half. So see where the sine is 1/2, that's the y value, sine is 1/2. Now if I switch my calculator to mode radians, and now if I put the sine, instead of 30, I put pi over 6. I still get a half. Okay? So in this discussion, it says to ask students to summarize the main points of the lesson, either in writing or to a partner or as a class. So here's what we should come up with as a total. A radian is the measure of the central angle of a sector of a circle with arc length of 1 radius length. If there is no degree symbol or specification, then the use of radians is implied. There are 2 pi radians in a 360-degree rotation, also known as a turn. So degrees are converted to radians and radians to degrees by 2 pi radians equals 1 turn equals 360 degrees. From this point forward, all work will be done with radian measures exclusively for rotation and as the independent variables in the trigonometric functions. The diagram is nearly the same as the one for the sine and cosine functions in lesson 4, but this time it is labeled with rotations measured in radians. Use the diagram to find cosine of 7 pi over 6 and the sine of negative pi over 6. So 7 pi over 6 is right here in red, and it said cosine, so that's your x value, so it's negative root 3 over 2. And find the sine of negative pi over 6. Well, pi over 6 is here, so negative pi over 6 equals positive 11 pi over 6, and the sine of that is negative 1/2. Okay, page 7 brings us to the end of lesson 9. Review this lesson summary and go to your problem set.